Hey everyone, Pierre-Alexandre here from Utrecht University and MIT. And in today's video, we're gonna do is to analyze some basic local indicators. So basic local network indicators refers to the specific position of nodes in the network. So for instance, think about the most classic one, the most intuitive one, which is just degree. So degree will tell you something about the position of nodes in the network and just tells you to how many other nodes they are connected, right? So if you have like 5 friends, then your degree centrality is going to be 5. That's as simple as that. Okay, so I'm doing a bit of cleaning here, so you see also how to do that. We take again our data set of Les Miserables, in this case. We create a G-object, and as I was saying earlier, once you have this G-object, it becomes very easy to do some kind of basic network analysis. So we have our G-objects, and first thing we're going to do is to compute our degree centrality of actors, and you see, it's going to give me a vector where I have the number of actors that my focal node is connected to. So that's going to be with the function degree, and in the argument of the function, I'm going to put the name of my graph object, which is G. Now, you can also have a normalized version if you prefer. And then what you have to do is just pass the argument normalize equal true. And maximum is going to be 1 in this case, because we divide by the maximum number of actors. Okay, so maximum is going to be 1 here. That's to compute the normalized version of degree centrality. What we're going to do next is to compute closeness centrality. There is an easy way to do that, but before we do that, I want to make sure that you really understand how it works. So we're first going to create a matrix that will give you the shortest path of my graph. So here I create a matrix called S, and I use the function shortest path, and in the argument of the function I use G. So let's look at our matrix. So you see it's a 77 by 77 matrix. That's the dimension of my matrix. And what I see is that Gillenormand here needs 3 steps to connect to Zéphine. So it has to go through first node, then the second one, and then finally it can reach Zéphine. So that's the matrix of geodesic distance, or the matrix of shortest path between any 2 actors in the network. And the closeness centrality will basically be 1, because we want a measure of centrality, not a measure of distance. So we're going to divide 1 by the overall sums of the overall distance in the geodesic distance matrix. Simple as that. So that's what we get. And if you want to compute it more quickly, once you understand how it works, so you can really explore your matrix S to really understand how it works, then what you can do is closeness and G. And then that becomes very easy, and you get basically the same results. Now you can also measure, try to see whether some actors are brokers in the network, so whether they lie very often in the shortest path of other actors. And to do that, you compute the measure of betweenness centrality. So that's how you get it. So you have 4. We have the big 4. So we have degree centrality. We have closeness centrality. We have betweenness centrality. That's 3. And the 4th one, which is also the one that Google used to rank web pages, is eigenvector centrality. So to compute this one, you're gonna use eigenvector centrality here, measure, then put G, and then you're gonna extract the vector, because we want the vector part of the eigenvector. So we extract the vector part, and that's what you get here. And remember, the meaning of eigenvector centrality is basically telling you whether you are connected to central nodes. So this measure takes into account the centrality of other nodes to report the centrality of eigenvector centrality. So what we can do, if you want this big 4, you can basically create a data frame, if you want to have all of them together. To do that, you use the data frame function here. And then we're going to name our first column C. So this one is going to be degree G. So that will give me a column with the degree centrality. Then I will have second column with betweenness centrality. I'm going to use the function betweenness of iGraph. Then a third column that will give me closeness centrality. So using the closeness, there you go, closeness measure here. It's going to be for closeness centrality. And the third one is this eigenvector centrality that we just computed a few minutes ago. So if I do that, I'm basically creating a data frame that summarizes the big four, and you can explore it here, or you can look over there, and then you get all your different measures of centrality, and you can compute them. All right, so I encourage you to play with this different indicator.